Welcome students to the sixth lecture of Logic and Distributed Control System. So today we are going to discuss PLC as a system. Last class we have discussed as an introduction of programmable logic controller. So today we want to know that what are the integral components of a PLC are. So now this is the overall PLC system, where we can see that the major parts of a PLC system are the central processing unit, that is CPU, the input output section, and the power supply and the programming devices. So here in the figure you can see the central processing unit consists of memory, program and data, and as well as the processor, where you can see that the central processing unit is connected with the input module, and also it is connected with the output module. The input output module along with the central processing unit is powered by power supply module, and the programming device the external CPU or the computers are connected with the PLC module, that is CPU. Now PLC, definitely we can treat PLC as a computer, but PLC is a computer but different from the one probably used for sensing and working with. So now whatever the computer we are using, how the PLC is different from that computers. So there are two kinds of computers: data processing computers and process control computers. So this figure will tell you that what is the difference between the data processing computer and the process control computer. So the data processing computer, the typical inputs received by these data processing computers are from keyboard, pen, mouse, etc., and the output devices which are connected to this data processing computers are the video display terminal, printer and plotter. But in contrast to that, if you see the process control computer, the input received for this process control computers are the motion sensor, sound sensor, heat sensor, light sensor. Means the different sensor the input is coming to the process control computer, and the computer is going to drive the outputs. They are the motor, solenoid, heater and lights. So in this way a data processing computer is going to differ from the process control computer, and the PLC is typically a process control computer. Now once again, if you see the overall PLC system, where we are observing that the CPU consists of the microprocessor, memory and where which is interfaced with the programming device or monitor, and also the input module is connected with the CPU and output module is also connected with the CPU, and they are sitting inside the rack and chassis. So PLC are type of process control computers, small, relatively inexpensive, environmentally hardened and easy to program, operate, maintain and repair. So the conventional PLC architecture, if you see, the PLC is essentially a microprocessor based real-time computing system that often has to handle significant IO and communication activities, bit oriented computing as well as the normal floating point arithmetic has to be performed by a PLC. A typical set of components that make a PLC system as shown in the figure. So these are the essential components which will be connected with the CPU, and this whole unit is representing a PLC system. So the four major units of PLC system we are going to discuss one by one. First is the CPU, the brain of the system, which has three subparts. They are the microprocessor, memory and power supply. The computer center that carries out the mathematical and logical operations is the job of the microprocessor. Memory, the area of the CPU in which the data and information is stored and retrieved, holds the system software and user program, that is the work of the memory. And power supply, the electrical supply that converts the AC line voltage to various DC values. In the process, the power supply filters and regulates the DC voltages to ensure the proper computer operation. Now pictorially it has been shown that the three major components of the CPU, that is processor, memory and power supply. And in this figure you can see that the CPU is connected with the input module and output module, and which is powered by the power supply, and the memory where we used to write the user program. Now another important component of the PLC is the programmer or monitor, that is PM, is a device used to communicate with the circuits of the PLC. Handheld terminals, industrial terminals, and the personal computer exist as a PM device. So we can use the personal computer or we can use the handheld device as a PM. Now a programming device, that is why the programming devices are required. A programming device is used to enter the desired program into the memory of the processor. So this handheld device or by the computer you can enter the desired program into the memory of the processor. So the program is entered using the relay ladder logic programming language. So we used to write the ladder logic as a programming language for the PLC. But other than this ladder logic, the languages are exist for the PLC. The personal computer is most commonly used the programming device. Why? Now the computer monitor is able to display more logic on the screen, thus simplifying the interpretation of the program. So it is very easy to debug as well as easy to write, because the computer monitor is wide, so we can see major portion of the program, but which is not possible for these handheld devices because its display area is very small. Third component is the I/O module. The input module has terminals into which the electrical signals generated by sensors or transducers are entered. The output module has terminals to which the output signals are sent to activate relays, solenoids, various solid state switching devices, motor and displays. And fourth component is the rack and chassis. The rack on which the PLC parts are mounted and on which the CPU, programming monitors and I/O modules are mounted. Now there are two kinds of I/O architecture is found in the market. That is, fixed I/O is typical of small PLCs that come in one package with no separate removable units. The processor and I/O are packaged together. So here no flexibility of modular fashion you will get. Instead of that, you will find that all the components of the PLCs are fixed and they will come in a package. You cannot separate, or even if suppose if you want to extend the number of inputs with attaching a separate input module, which is not possible in case of fixed I/O. But in contrast to that, in case of modular I/O is divided by compartments into which separate modules can be plugged. This feature greatly increases your options and units flexibility. Means suppose for the maintenance purpose, if some module has to be removed, it can be separated very easily. Or if suppose input output modules are to be extended, and that extended means suppose if you want to increase the number of inputs and number of outputs, that also can be easily added with the modular I/O. Now we will see that how the central processing units are working. In small PLCs, the processor, solid state memory, I/O modules and power supplies are housed in a single compact unit. Means in case of fixed I/O, what I said. The programmable device, usually a handheld unit with a keypad and LCD, is separate but tethered to the main unit with a cable. In large PLCs, the processors and memory are in one unit, the power supply in a second unit, and the I/O interfaces in a modular fashion. It is attached with it in a as an additional unit. The programming device, which is maybe a PC, is of course a separate but tethered item. Now, if you see the operational sections of a PLC, you will find that the memories are there, and memory may be fixed memory and alterable memory, where you can see that in the fixed memory where the logic, edit, monitor, communicate, etc. will be written, programming for this will be written, and the diagram, numerics, function status, IO status will be handled or stored in the RAM. And the processor is used for the logic, clock and mathematical operation. Along with that, it is going to interface with the input modules, output modules, and the keyboard, monitor and other peripheral devices. And there are different kind of memory chips are used in PLC. They are the ROM, RAM, PROM, EPROM, EEPROM and NOV RAM. They are used in case of PLC CPUs as a memory. And there are wide range of processor exist um, for the PLC, and they are starts from 8085 to the Pentium. So the clock speed may vary from 1 megahertz to 1.2 gigahertz. So all computer processors are designed to carry out arithmetic and logic operations. Although some high-end large PLCs use the Pentium chip, most are content to operate with less powerful microprocessor. Some small PLC functions quite nicely with 8-bit microprocessor running at 4 megahertz, and slower microprocessors are used because they proven reliable. Many processor programs have been written and debugged, and most processors changes so slowly that a fast processor is overkill. Means to synchronize with the slow processes, we require the slow processors. So that's why you will find that most of the PLCs, the 8-bit microprocessors are sufficient for the operation. And now if we want to know that how the CPU processors are working, then this diagram will be helpful to us. So we have a RAM in the CPU processor with the fixed operating system program, and which is going to give the instruction to the control section, and which consists of the arithmetic logic unit with few registers and the control unit, which is going to help to analyze these blocks, where we are finding that the different peripheral devices, keyboard, video terminal unit, tape, print, discs are interfaced, and also the input scan block is present, which is connected with the input module, and the information gathered from the input scan block along with the inputs what we are getting from the other connected devices are going to logic scan program, where program user writes for process control. So here in this area the programming has been written, and then with this block the output scan block is connected, where the output modules are connected, and along with this logic scan block the interface with other CPUs or computers are also connected. Now we want to understand that how the processor is going to work. Now a ROM with fixed operating system program interfaces to the control section. The unalterable program manages the operation of the PLC. Whatever the logic scan user program is asking PLC to do, the operating system program is there to do. So here basically you have written the user programming. So whatever this programming is going to tell to the PLC to do, the operating system program is there to do. The control section, the heart of the microprocessor. So this is the control section, which is the heart of the microprocessor, consists of a control unit with a clock, ALU and few temporary storage register. The control section determines which operating sections are to be functional in what order and how long. The input scan block when called upon to operate. So now if suppose the control section decided that input modules has to be read, means suppose whatever the input status are there, so different inputs are connected, they are changing their status either on and off. So suppose that has to be read, so then the control section is going to give command that now we have to read the input status. So that's why the input scan block when called upon to operate, the scans the inputs and places the individual input status to the RAM memory. After analysis, the logic scan, where the user logic ladder program is written, updates the output scan block to the appropriate state. Next, the outputs are scanned and updated. The output statuses are changed or left alone depending on logic analysis. Output status depends on the output status depends on the output status signals of the CPU. Now here you see one typical diagram has been shown where you can see that the two power rails are connected with the PLC, that is L1 and L2, which is giving power to the input and output devices along with the PLC. And now the input devices are hardwired with the PLC and output devices are also hardwired with the PLC. And you see this is a PLC which having 8 inputs, that is 0 to 7. So this representing the status of the input. These lights on the PLC will show you that the status of the input, and these 6 outputs are going to show you, this is the LED lights are going to show you the status of the output, and these are going to give you several indication like power, run, okay. Now though it looked like that the input and output devices are physically connected with the CPU or the PLC, which is not in the reality, we will see that the input and outputs actually not directly connected with the PLC. Instead of that, they are optically isolated. That module we are going to see shortly. So programmable controller IO connection diagram showing no physical connection between the inputs and outputs, but this figure actually help you to understand how the ladder programming has been developed. Here you can see that two rails are there, which is basically the power lines L1 and L2, and the input and outputs are connected through rungs of this ladder. So exactly this figure we are going to mimic in the programming, so that's why it is known as ladder programming. But here one thing I want to mention, that ladder programming is not the only language by which we can do the programming in the PLC. Other languages are also there, that definitely we will discuss in the next class. So PLC inputs are also very important. We want to know that what are the inputs are present. The input interface is the electronic circuitry which connects the PLC input terminals to the processor. The typical input signal to the PLC are provided from limit switches, which may use to detect the travel of a piston, photocells used to detect the presence of a component, guard switches used to detect if a guard is in position, push button used to start or stop a process. And analog sensor, proximity detectors, Hall effect switches may also provide the inputs to the PLC. PLC is only concerned with the on-off signal at its input. So the devices which having which is capable to generate the on-off signals, that can be used as a inputs to the PLC. So the typical figure is going to show you several inputs, that is input devices such as push button, limit switches, sensors are hardwired to the input module terminal. Okay, so now there are several symbols of the switches you can see, which is NO, NC, SPST, SPDT, SPST and DPDT. So here NO is representing the normally open, NC is the normally closed, and SPST is the single pole single throw, SPDT is the single pole double throw, SPST representing double pole single throw, and DPDT is the double pole double throw. And most interestingly, you see we are going to use the NO and NC, the normally open and normally closed push button switches, and their operation is like that. The NO push button switch is normally open. When you are going to give or a push, then it is going to close, and it will be closed as long as you are pushing, and if you release it, then again it is going to be normally open. But in case of normally closed, it is closed normally, and when the push has been given, then it is going to open and no current is going to flow. And how long it will be open? As long as you are giving the push. If you withdraw it, then again it will come to its normal position, that is normally closed. And this concept will be very much useful to develop the programming in case of PLC. So now we will understand the PLC input interface, because we have claimed that the inputs are not going to be connected with the PLC directly. So how they are connected and what are the interfacing facilities are there in case of PLC. The interface has to convert input voltages 120 to 240 volt AC or DC from these input devices to low level DC voltages, typically 5 volt to 12 volt, that is used in the processor. The interface also has to provide electrical isolation to prevent noise and voltage spikes on the input lines from destroying the input signals or even the input circuits of the PLC, or the extreme cases the processor itself. So the isolation is provided using optocouplers or opto-isolators. So this is the typical DC interface. So now suppose a switch is there which is representing the input status of the system. Now when it is going to close, then means the current is going to flow. Now here you can see that a light emitting diode is there, and when the current is going to flow, then depending on the status of the switch, the light is emitted by the LED, and this signal is transmitted as a rays of light and falling to the base of the phototransistor, and then phototransistor will be in a conduction mode, and which is going to give the signal to the processor. So in this way the status of the input is going to the processor or the CPU, where you can see that this switch is not connected directly with the CPU. Instead of that, it is isolated physically by opto isolator, and the transmission of signal is through the light only. So the optical isolation is achieved using a LED as a transmitter and phototransistor that acts as a receiver. When an input device, that is switch, is activated or closed, the LED is turned on, the light emitted from the diode is picked up by the phototransistor and a signal sent to the processor. So this is the way the isolation has been done. And what is the facility of this isolation? Now, the surge voltages produced by the input section is not going to directly hamper the CPU or the PLC. So the damage in the extreme case will be that the LED will be burned out if the limiting voltage is going to be exceed. So the surge voltages are, or the input noises are not going to affect the PLC processor. And a typical AC input interface, where you can see that a typical input module has 4, 16, 8, 12, 16 or 32 terminals. It means that we may have the 16 input, we may have the 32 inputs, or we may have the 4 inputs, and each of the inputs, this kind of module has to be developed. How? Now with a input, now we know that suppose its voltage is 120 volt, but the CPU cannot accept this high voltage. Then what we have to do, and also it may be AC voltage also. So AC voltage cannot be accepted by the CPU. High voltage as well as the nature is AC. So that's why we have to use a converter, and this converter is going to convert this AC signal to the DC signal. And to limit the voltage, we can have the Zener diode, which will produce the fixed voltage which is acceptable by the CPU, and also that voltage is not directly sent to the CPU. Instead of that, we are using a opto isolator, which is going to send the status of this input signal through light. So already the working principle of the opto isolator we have seen. And if you have the 4 inputs, then this kind of 4 module has to be present to interact with the CPU from the input terminal. So now we can see that the first block receives the input signal from the switch, sensor and so on. The AC voltage input, the DC converter consists of rectifiers and a means to step the voltage down a usable level, usually with a Zener diode we will use. Now there are several output devices are also in the PLC. They may be solenoid actuator, mechanical relays, motor, stepper motor, pilot lamp, etc. And these output devices also will be hardwired with the PLC, but they also will be physically isolated, and also some interfacing circuit will be there with the PLC output. So output devices such as motor, starter, solenoid valves and indicator lights are hardwired to the output module terminals. Now you see here a typical output module has been shown. Now the output module operates in the opposite manner from the input module as seen in the block diagram. So how it is working? Now suppose a 5-volt signal is coming, plus 5-volt signal is coming from the CPU, and which is typically a DC voltage. Now we know that suppose this voltage, what it is produced by the CPU, with that we want to drive a AC motor. Then what we have to do, now this 5-volt signal is transmitted through the opto isolator to the converter, and now with some converter mechanism we are going to convert this DC signal to the AC signal, and also along with that we are going to step up the voltage with the required arrangement. So this has to be done for each of the output what you are dealing with the PLC. Now we will come to the power supply. The power available is most plants is 120 volt AC or 60 Hertz. Most PLC operate on plus 5 volt or minus 5 volt DC. Therefore, the PLC CPU must contain circuitry to convert the 120 volt AC input to the required 5 volt DC values. The conversion is accomplished by a built-in voltage converting power supply, and this is the power supply arrangement you will find in a typical PLC, where you can see that line voltages has been converted with the converter rectifier with a ripple DC, and ripple DC has been filtered out to get the pure DC, and then the regulator has been used to get a particular voltage like 5 volt DC or minus 5 volt DC. So this is the block diagram representation of power supply. And now we will see the last component, that is the rack. It is called the modular because the rack can accept many different types of IO modules that simply slide into the rack and plug in. Okay, and so let's start off by removing all our modules and leave us with a naked PLC and with only the power supply and rack, and then we want to see that how it look like. So this is the typical picture. You can see all the input output module, CPU has been removed, only the power supply section is there. Then you can see how the naked PLC will look like. So the rack is the component that holds everything together. Depending on the needs of the control system, it can be ordered in different sizes to hold more modules. Like a human spine, the rack has a back plane at the rear which allows the cards to communicate with the CPU. And the CPU will look like typically like this. The brain of the whole PLC is the CPU module, which consists of memory, then integrated circuit, microprocessor and battery backup. And this is a typical IO module will look like if you open the door that is of each rack. The IO system provides a physical connection between the equipment and PLC. Opening the doors of an IO card reveals a terminal strip where the input output devices are connected. There are many different kinds of IO cards which serve to process several types of inputs and outputs, so the CPU can use it for its logic. It's simply a matter of determining what inputs and outputs are needed, filling the rack with the appropriate cards, and then addressing them correctly in the CPU program. So when we are going to do the programming with these inputs and outputs, then we should give a proper address system or proper addressing system has to be generated to address each and every input connected to the PLC. So that we will do when we will discuss the programming part. So PLC versus computers. So now we will end with the PLC versus computers. So we want to know that what are the difference between the PLC and the general purpose computer. The architecture of a PLC is basically the same as that of a personal computer. Unlike PCs, the PLC is designed to operate in the industrial environment with wide ranges of ambient temperature and humidity, but the general purpose PCs are used in a sophisticated environment. A properly designed PLC installation is not as affected by the electrical noise inherent in most industrial locations. So you will find that the industrial locations will be full of electrical noise and in magnetic interference or electrical interference, but PLCs are developed in such a way that they will be not influenced by these interferences. And unlike the personal computer, the PLC is programmed in relay, ladder logic or other easily learned languages. The PLC comes with its program language built into its memory and has no permanently attached keyboard, CD drive or monitor. So this is the difference between the general purpose computer and the PLC. The computers are complex computing machines capable of executing several programs or tasks simultaneously and in any order. PLC execute a single program in an orderly and sequential fashion from first to last instruction. So these are the difference exist between general purpose computer and the PLC. So I will stop here, and in the next class we will discuss about the what are the different languages are available to program a PLC. Thank you.